Hello everyone, in this video lecture we will discuss about inverse power method. So inverse power method is used to compute smallest eigenvalue of the matrix A. Like suppose if lambda is the eigenvalue of a matrix A with eigenvector V, then we can write it as AV equal to lambda V, and let's apply A inverse on both sides. Then we are getting A inverse lambda V. Lambda is a scalar that we can take outside, so it can be written as lambda A inverse V equal to I V. Finally, we can write it as A inverse B equal to 1 upon lambda V. So this implies that 1 upon lambda is the eigenvalue of matrix A inverse. So if lambda is the eigenvalue of the matrix A, then 1 upon lambda is the eigenvalue of the matrix A inverse. Suppose lambda 1, lambda 2, lambda 3 are the eigenvalue of the matrix A, then 1 upon lambda 1, 1 upon lambda 2, 1 upon lambda 3 are the eigenvalues of the matrix A inverse. Okay, so if lambda 1 is the maximum eigenvalue of the matrix A, then 1 upon lambda 1 is the smallest eigenvalue of the matrix A inverse. So by using this concept, we can apply inverse power method to compute the smallest eigenvalue of the matrix A. So let us do one example. Use inverse power method. Use inverse power method to compute smallest eigenvalue of matrix A with initial vector as 1 1 1, suppose, where the matrix A is 1 2 3 0 1 4 and 5 6 0. Okay, so by using inverse power method, we compute the smallest eigenvalue of the matrix A. So what we do here, we will compute the largest eigenvalue of the matrix A inverse. Okay, so compute first A inverse. Let us suppose A inverse we are representing by B. That is what it is coming out to be: minus 24, 18, 5, 20, minus 5, minus 15, 4, minus 4 and 1. This is the inverse of the matrix A. Now we will apply power method to compute maximum eigenvalue of the matrix B. So apply power method to compute maximum eigenvalue of A inverse matrix, that is equivalent to B. So let's apply power method here. So initial vector given as 1 1 1 transpose. So y1 we can take as bx0. B is the inverse of the matrix. Bx0, what we are getting, that is minus 1 1 0. We can write it as 1, but is the maximum value 1 in this vector y1, so we can write it as minus 1 1 0. So this can be represented as lambda 1 that is the first approximation to the eigenvalue, and vector x1. Okay, now we will compute y2. Y2 is what? That is bx1. Bx1. X1 is the vector that we normalize. So what is coming out to be? Bx1 is coming out to be 42 minus 35, 9. Okay, out of these entry in y2, maximum value is what? That is 42. That is 1 minus 0.8333, 0.2143. Okay, so this is what the element that we are taking, that is the maximum element in the battery y2, that will take outside, that is represented by lambda 2, and this vector is what? That is x2. Okay, x2 is what? That is the normalized vector. So this lambda 2 is the second approximation to the eigenvalue. Okay, and we will continue and we'll get the maximum eigenvalue when to this value, that is 41. Okay, now we will come, since this is not less than epsilon, let us take the tolerance in this example. Let us take tolerance here 10 raised to power minus 3. Okay, so whenever this condition is satisfied, we will stop. Now compute y3. Y3 equal to b x2, coming out to be here minus 37.9286, 31.6429, and this value is minus 8.1190. Out of this, the maximum entry is what? 37.9286. We are interested in the numerical largest eigenvalue of the matrix A, so that's why we can write it as, we can take the maximum value out of this, that is 37.9286. So what is coming out to be here? 0.8343, and this is minus 0.2141. Okay, so this is your lambda 3 and this is your x3. Let's compute y4. Again we will check whether the condition is satisfied or not. The difference between the consecutive eigenvalues is less than tolerance or not. If it is so, then we can stop. Okay, so let us check what is the value coming out to be here. Lambda 3 minus lambda 2 is coming out to be 4.0714. Not less than epsilon, so we will continue. We'll compute the value of y4, that is bx3. Okay, so the value coming out to be minus 37.9466 minus 31.6579, 8.1230. Okay, out of this, the maximum value is what? 37.9466. The value is 1 minus 0.8343, and this value is what? 0. This value is coming out to be here 1. This is minus 1.8343, and this value is minus 0.2141. Okay, now compute lambda 4 minus lambda 3. This is coming out to be what? 37.9466. This is 37.9466. Third lambda 3 minus lambda 2. It is coming out to be 0.0181. It is not less than epsilon. We will compute y5. Y5 is what? That is bx4. Okay, so this is your lambda 4 and this is your x4. The value is coming out to be what? Minus 37.9466, 31.6578, third value is minus 8.1230. 37.9466 1 0.8343 minus 0.2141. Okay, this is the value lambda 5, this is x5, and the difference if we'll compute lambda 5 minus x lambda 4, it is coming out to be 4.1944 into 10 raised to 4 minus 5 less than epsilon, that is 10 raised to 4 minus 3. So lambda 5 is the maximum eigenvalue of the matrix B. Okay, so what is this value? So lambda 5 is what that we computed, that is 37.9466. Then the smallest eigenvalue of the original matrix A is what? 1 upon lambda 5, that is the fifth approximation, that is 1 upon 37.9466. So this is your answer. So this is the inverse power method. It is used to compute maximum eigenvalue of the any matrix B. So since we want to compute here the smallest eigenvalue of the matrix A, for that we have compute the inverse of that matrix, okay, and then applied power method. So we obtained the maximum eigenvalue of the matrix of the inverse of the matrix, and then again in order to compute the smallest eigenvalue we are taking the reciprocal of that eigenvalue. So that is the inverse power method. Let us finish it here.